Hello, in this section you will learn how to program the EEPROM available in the AVR microcontroller. You will understand how to use the different registers to configure the EEPROM for read, write and erase operations. And we shall develop a driver software. You shall use two different design approaches to implement the driver. Almost all AVR microcontrollers have internal EEPROM for semi-permanent data storage. Like flash memory, EEPROM can maintain its contents when electrical power is removed. The Atmega 328 microcontroller contains 1 kilobytes of EEPROM memory. EEPROM stands for Electronically Erasable Programmable Read-Only Memory, which is a type of non-volatile memory used in various electronic devices to store relatively small amount of data. The EEPROM allows the data to be read, written and erased at byte level. In the most variants of the AVR architecture, this internal EEPROM memory is not mapped to the addressable memory space. It can be accessed as an external peripheral device using special registers with read and write instructions. This makes EEPROM access much slower than the data and program memory. The AVR CPU cores uses 3 I/O registers to interact with the EEPROM. These are EEPROM address registers high and low, that is EEARH and EEARL. The EEPROM data register, that is EEDR. EEPROM control register, EECR. Let's look into the details of these registers. EEARH and EEARL are the two registers used to address the byte location in the EEPROM memory space. The Atmega 328 microcontroller has 1 kilobyte of EEPROM memory, so the lower 10 bits of the register pair is used for addressing. The rest of the bits, that is bit number 11 to 15, are unused. The initial value of these registers are undefined and must be written with the correct address value before accessing the memory. The offset of EEARH and EEARL is 42 and 41 in hex respectively. This offset is used with load and store instructions. The offsets 22 and 21 in hex should be used when accessing the register in I/O mode, that is, when the registers are used with in and out instructions. In the write operation, the register EEDR must be initialized with the data to be written to the EEPROM memory. After the register is loaded, instruction is issued to transfer the data from EEDR register to the EEPROM memory at the address specified by the address register pair. For the EEPROM read operation, the EEDR contains the data read out from the EEPROM memory address. The offset of the register is 40 in hex, and the hex value of 20 should be used in the I/O mode. The register EECR is used to specify the operation to be performed on the EEPROM memory. The offset of 3F in hex is used to access the control register while using load and store instructions, and the offset 1F in hex is used with in and out instructions. Now let's look into the details of each bit in the control register. The EEPROM programming mode bits, that is bit number 5 and 4, is used to select the programming action when EEPROM program enable bit, that is EEPE, is set. The microcontroller supports three different programming operations. Writing the bits with the value 00 causes the EEPROM to be erased and written with the new data in an atomic operation. This programming mode takes 3.4 milliseconds to complete the operation. The erase only operation is triggered by setting 01 to these bits, and the value 10 triggers the write only operation. The individual erase only and write only operations takes 1.8 milliseconds each. The write to the EEMP bits is ignored when EEPE bit is set. Writing 1 to the EERIE bit enables the EEPROM ready interrupt if the I bit in the status register is set. Writing 0 to EERIE bit disables the interrupt. The EEPROM ready interrupt is generated continuously when EEPE is cleared. This is an important consideration while designing the interrupt-based EEPROM driver. The EEPROM master program enable, that is EEMPE bit, determines whether writing 1 to EEPE causes the EEPROM to be written or not. When EEMPE is set to 1, setting EEPE within 4 clock cycles writes data to the EEPROM at the selected address. If EEMPE is 0, setting EEPE will have no effect. When EEPE has been written to 1 by the software, hardware clears the bit to 0 after 4 clock cycles. The EEPROM write enable signal, that is EEPE, is the write strobe to the EEPROM. When address and data are correctly set up, the EEPE bit must be written with logic 1 to write the data into EEPROM memory. The EEMPE bit must be written to 1 before EEPE is written to 1, otherwise write operation does not take effect. The EEPE bit must be polled before initiating the read operation. If a write operation is in progress, it is neither possible to read the EEPROM nor to change the address registers. The EEPROM read enable signal, that is EERE bit, is read strobe to the EEPROM. When the correct address is set up in the address register, the EERE bit must be written with logic 1 to trigger the read operation. The EEPROM read access takes one instruction and the requested data is available immediately. When the EEPROM is read, the CPU is halted for 4 clock cycles before the next instruction is executed. With this, I conclude this lesson. See you in the next lesson. Until then, keep learning.